Great. So I realized I had, the longest title, right? And thanks, Brian, for actually repeating the entire title. So I decided to rename the talk to provide something less confusing, but maybe still confusing, which is how to build a shielded contract wallet. So hopefully everything will make sense at the end of the talk. But let me get started. What are we doing here? So the goal here is to think about privacy for Ethereum. Privacy is, at the moment is a very controversial topic, of course. So I'm not going to touch on the why of this, right? So, because it's require hours to really discuss this. But the bottom line is, we need to have privacy-preserving technologies on blockchains before we can see wide-scale adoption, right? So let's start with the what. So what do we mean by privacy with Ethereum? So first, let's see, let's do a recap of what Ethereum is. By Ethereum, I don't just mean the blockchain, I mean the entire ecosystem, right? Where dApps have smart contracts on their backends and white pages at their front ends for now. And we'll have users that use wallets to interact with these dApps through the front end and sending transactions to the blockchain via some intermediary, probably some validators like Infura. And now, let's talk about privacy, or the lack thereof, right? So if you go into Etherscan, you'll be able to see a list of transactions completely in public. And if you click on it, you'll see exactly the originator of this transaction and the contents of the transaction, right? So everything on Ethereum is transparent. And the first notion we'll define for this talk is anonymity. We mean that a transaction is anonymous if the sender is somewhat hidden, right? So in this case, you can think of maybe the address is just completely scrambled or fixed, where a group of users can share the same address. And the second notion is confidentiality, right? We say that a transaction is confidential if the contents of the transactions are completely hidden, right? It's very, very simple notions. And as it turns out, the confidentiality is actually really, really hard to get on public blockchains, right? So because we want to do computational shared state in smart contracts, so therefore, we either require trusted third party to run computation off-chain in zero knowledge, or more complicated techniques like homomorphic encryption or MPC, or trusted hardware to do this. So for this talk, I'm not going to be talking about confidentiality. I'm purely going to be talking about how to get anonymity for Ethereum applications. So I think my slide is a little bit lagging behind. Let me actually make sure I'm on the right slide. So actually, anonymity is really easy on Ethereum. If you have used any mixer running through the pool, you're able to withdraw from it every single time you want to do any smart contract transaction, and then deposit the tokens back, right? So if you do this religiously for every single time you want to use Uniswap, you want to use OpenSea, you're able to do this, right? Assuming that the mixer supports arbitrary denominations of arbitrary assets. However, this is very, very hard to use, right? Because you have to keep track of all your temporary wallets every single time you do anything, that should be in its own context. So the goal is to do something that's, similar to this, have a similar anonymity guarantee, but very user-friendly and easy to use. So let's look at what solution we have today, right? So here is the Ethereum ecosystem. We have the L1, we have a bunch of side chains or L2s, and a bunch of applications on top of these chains. And we have mixers, of course, on Ethereum, and other privacy-preserving tools like Railgun, and some tools like zk-Proof from the Ethereum Foundation and Aztec, which kind of aim to do both, position themselves both at the layer 2 and the privacy solution. And of course, we have kind of like side chains that kind of, some of them are compatible, are building on top of Ethereum, and some of them are building completely different chains. And so it turns out that, so Railgun and zk-Proof, if you go to what they actually do, they only do peer-to-peer swaps on top of payments, right? So there's no notion of interacting with a smart contract application that's on Ethereum. And these applications circled in blue actually have some type of DeFi interoperability. So for Aztec, you're able to use a handful of 4 to 5 applications that's on the Ethereum L1. However, none of them actually supports most of the smart contract applications, right? So they usually it's a whitelist, meaning they need to. So for Aztec, for instance, the Aztec Connect bridge, each contract needs to have a specialized interface to support Aztec transactions, and every single user transaction needs to be aggregated before they are processed on the L1 application. So the goal is to really to ask, can we build something that's better, right? And so let's talk about what are we trying to build. So I'm going to explain the terms that's title of my talk. And so first, what I mean by feature complete. Feature complete means that our privacy layer should support interaction with any smart contract, right? So the user should be able to submit any sequence of smart contract calls and have them carried out from an address that actually own assets. And second, users should be able to prove statements about what they own, right? So so currently on transparent Ethereum, you just simply send your address to someone else, and they can see exactly what you have done. But once we're in the privacy layer, we should be able to prove verifiably what we have done, what we have owned currently, right? And second, it should be backwards compatible. And so this is something that would be nice to have, because we'll have a vast ecosystem of existing dApps in Ethereum. And it would be nice to not have to rewrite all of them for privacy-preserving system. And finally, of course, we want anonymity by default, meaning every single operation should be anonymous. And so now let's talk about how we're going to do that. So if you look at these three features, roughly they can be broken down into two sets, right? So at the top here, we have something that's essentially what a smart contract wallet support, right? It supports interaction with any dApp, and you can disclose what you have. And on the bottom here is what a shorted pool offers you, right? What a mixer does, which is it gives you some anonymity, but it's hard to use if you want to use it on dApps. And so what we're going to do is we're going to combine the two, right? And so you can think of we want to take a shorted pool, right? With Merkle trees and general proofs. I want to take a smart contract wallet, and we're going to put them in the same contract, and we're going to try to make things work. Okay, I'm going to pause here very briefly because it's really cute and neat idea of a way of explaining this, which took me roughly half a year to get to this point. Okay, so let's actually try to understand exactly what these things are. So first, shorted pools. Since this is an applied ZK workshop, let me go more into detail of how these things work. So first, we'll have the notion of addresses and splitting keys, right? So these doesn't have to be Ethereum addresses, but usually there could be some public key and a secret key that you can use to sign. And usually a shorted pool will store a set of nodes, which each will store an address, the owner, and a type. This could be ERC20, 721 address, and the amount, which is how much is stored in this node. And we'll have a notion of node commitment to not store this in the plane. And usually the state of the shorted pool is stored inside a Merkle tree, meaning we commit to all the set of node commitments that's ever added to the system inside an incremental Merkle tree. But how do we actually spin nodes, right? So usually nodes are spent via nullifiers to preserve anonymity, so to not link deposits to withdrawals. And so to spin the nodes, you will reveal a nullifier that you approve is committed via the right manner via hashing. And now, so how do we fit this component together into a smart contract to have a shorted pool? Well, we simply store an incremental Merkle tree of nodes, a set of nullifiers, and a list of historical roots for our Merkle tree, right? And then we expose a couple of interfaces. So for deposits, we'll have the user submit simply a set of no commitments, right? And so this, and usually when users need to deposit to a shorted pool, the user actually transfers token to the shorted pool on Ethereum, and then the contract will verify that, and then insert the no commitments into the Merkle tree. And for withdrawals, there's something more complicated that goes on, which is that the user first need to specify a list of nodes that the user is spinning via the nullifiers. and you will give an aggregate amount and type, right? For if you take all the nodes, add the amounts up, assuming that the type is the same, what you'll get in a generalized proof. And then the contract simply verifies this proof, adds the nullifiers to the sets, and then transfer out the funds, right? And it turns out you can do something that's more complicated, which is that you can have transfers, right? So you can combine deposits and withdrawals and have computational transfers without revealing the amount in the middle. So hopefully this, everybody's familiar with this, or this is a good enough overview. But now let's move on to the second component, which is a smart contract wallet. So what is a smart contract wallet? Well, it is a smart contract that holds tokens, right? And that can carry out smart contract calls. So in particular, how a smart contract wallet works is that a user can submit any arbitrary sequence of smart contract calls to this smart contract wallet and have it interpreted on its behalf, right? So the user will submit usually some type of authentication, like a signature that the wallet will verify, and an arbitrary sequence of calls. And the wallet simply verify the signature and execute those sequence of calls on behalf of the user. Very simple. Now let's do let's just do them together. Like let's put the shielded pool and the smart contract wallet in the same contract. What do we have? If you see, so if we do this, naively, meaning we'll have one contract that interprets arbitrary calls and owns all the assets of everyone that's in the shielded pool, then what we get is that there's a vulnerability when, because user can submit any arbitrary calls, right? And this arbitrary calls can just transfer out the entirety of the token, reserves of the shielded pool, right? Because everyone shares the same shielded pool contract. So this doesn't work. Let's do something a little bit more sophisticated, which is that we will, split the contract into two parts. One is called the vault. One we call the wallet. The vault will actually own all the assets of the shielded pool, and the wallet now actually, it still records Merkle tree and so on and so forth, and will carry out the calls. So this is how it will work. So the user now needs to submit something that's additionally to make the entire thing work. So first, the user will submit a spend, right? And the second part is arbitrary sequence of smart contract calls, and thirdly, a return address to receive the output tokens, right? And the wallet will first verify that the spend is valid, and then request the funds from the vault. And the vault will verify that the request indeed comes from the wallet, and then carry out transfer out the funds that the user has proved that they spent. So this is usually in the form of a contract called to a token contract, because we're working with the ERC-20, 721, etc. And now the wallet. So now observe that the wallet has enough tokens for just this user operation, right? The user has unwrapped the tokens they want to spend in a smart contract call, and the wallet holds exactly those tokens. And the wallet then carry on the sequence of smart contract calls for the user. This could be calling Uniswap, going to OpenSea, buying NFTs, what have you, because it's arbitrary smart contract calls. And now at the end, the wallet can actually see what it holds at, in terms of tokens at the end, right? So you can return the entirety of leftover tokens back to the user to the address that was specified. Okay? And so there's some problem with this, which is that we have not done anything because this thing's not anonymous. The address right here as specified is fixed. Right? So we need to have some way of hiding who the user is, like who's actually receiving this refunds. So here's the change we're going to do. So usually in the shielded pool, the commitments is done in one shot, where we commit to the address, the owner, the asset type, and the amount in the commitments directly to go derive the no commitments. And we're going to change it to a two-step commitment, where we first randomize the address by hashing it with the randomizer to derive what I call the anonymous address. And then we're going to commit to derive the non-commitment, right? So notice that this first part, the bottom part, is computed by the user, before before everything ever goes on chain, right? They're just re-randomizing their address. And then the second part is actually computed by the contract, meaning the node commitment is actually not computed by the user, but we can insert any flexible type and amount during execution time of the transaction. And I'll note that there's other ways of doing anonymizations possible, and this is kind of like a naive way of doing it, which is not really efficient. OK, so now what do we get? We just simply have user randomize their address and then submit that instead for the refund address. And actually, there's a final last problem, which is that this zero vulnerability, because the layer here could actually essentially substitute the call and the return address to be anything arbitrary. There's nothing tying these three components together. So therefore, we actually need to change the proof in the first step to actually prove that the user did indeed authenticate the return address as well as the arbitrary sequence of calls. OK, so this is the final construction, which I find really neat. And it's entirely possible to implement on top of Ethereum today. And let me so this actually only gives the first feature, right, which is that we can use any token, any asset in a smart contract wallet and not reveal who the user is. However, we don't have verifiable disclosure, right? So we can't prove that I hold an NFT and I send a message, right? So to do that, we actually need to change how the nullifiers work. We need to actually insert the nullifiers in the sparse Merkle tree so that we can actually prove non-inclusion. So meaning that I have this token that have not been spent. OK, so what does this look like if you were to fully implement it? So as it turns out, if you fully implement this, you will for sure need to change how DApp frontends will work. Because how DApp frontends work right now is they'll get the address of the user, and then they'll pull the balance, and then construct transactions, which you just simply cannot use if you want an anonymous version of it. So therefore, we need to change the wallet frontend and the DApp frontend, as well as the APIs that allow them to interoperate. And as it turns out, that's actually the only change you need to do to make this infrastructure work. OK, so a bit of a background on this work. So this actually started out as more of academic work describing how you would do this on L1 natively. And throughout the past couple of months, we actually iterated on this to make it into a more backwards compatible version. And this is with help by Kyle from the Ethereum Foundation, as well as folks from the Equilibrium company. And so I would say that we'll have we'll have draft smart contract written as well as draft circuits. The contract is complete, written by Kyle, and it works. And you can write this sequence of transactions in ethers and submit it, right? So our prototype contract has about 17,000 constraints. And please come talk to me if you're interested in implementing this. We're still trying to recruit to actually make this project a reality. And I'll stop here for questions.
Sorry. A very nice talk. I think just want to ask a UX question, right? Because we are definitely facing similar issues here. I think one things we kind of struggling right now is that, let's say if you have a private asset, right? Like, are you reusing the existing Ethereum address system for the private asset, or you are kind of creating a new address system like Zcash's sharded asset? I guess I just want to say a little bit more. The reason I ask that is that, for example, we kind of find that in order to support, for example, a little bit more regulation compliance features like viewing keys, right?
Yeah.
It's really hard to reuse the asset, right? Or
yeah. So currently, the way that this works is that you have one sharded pool wrapping all assets, right? So I think for regular, that's the only way I think to make this work on existing Ethereum. You could redesign a different L1 to do something different. But for regulation compliance, I think you could do something that's more like espresso systems, where you build blacklists, or add the ability for asset issuers to freeze assets, and add ways to disclose what you have done, right? So you could add features to the sharded pool.
Gotcha. Thanks.
My question is, can this technology be used in ZK rollup?
Yeah. Actually, if you go back to the previous slide when I show what this looks like, this is for any EVM chain, right? So the point is, I think we should build scalability infrastructure and privacy infrastructure separately. This can be built on any ZK rollup, right? Like arbitrary throughputs, what have you, is actually better. And we deploy this privacy layer to any EVM, scalability layer.
Hi, could you go back to the final construction? What is the difference between steps 5 and 6, like leftover assets versus leftover tokens?
Oh, yeah. So step 5, what the wallet is inserting nodes back into its Merkle tree, right? So there's a record of who owns what inside the sharded pool, and there's a record of who owns what inside Ethereum, inside these tokens, token contracts. So step 5, the wallet is updating its Merkle tree to reflect that the user is getting those tokens back by constructing the nodes and inserting it back to the Merkle tree. And in step 6, the wallet actually needs to transfer these assets back to the vault because the wallet needs to start from a clean state for the next transaction.
Okay, thank you.
Hey, nice talk. I'm wondering if you want to interact with, let's say, Uniswap, or like receive funds in any way. Is there? I imagine that's a lot harder. Is there like a way to do that?
Uniswap?
Yeah.
Yeah, no, it's completely possible. Like this, Uniswap is just you need to start from an address that holds tokens, in terms of USD20, and you need to do a proof, and you need to spend, right? If you just construct those list of smart contract calls and give it to this protocol, it'll work. That's maybe I misunderstood the question, but.
Okay, yeah, I'm just wondering like how the step works where you can actually let's say funds go to the shielded wallet that's shared by everybody. Like how does an individual withdraw the correct amount? Like let's say that amount was not transferred by a user with a note, but that amount was transferred by a smart contract to the address of the shielded wallet. Like how does a user withdraw that? Yeah.
So at the end, so at step 5, the wallet. So there's something I guess skipped over, which is that the wallet needs to know the list of asset types to look at. So at the end, the wallet essentially goes through all the ERC20s and pulls its own balances. So like let's say I start from USDC and I want to swap to wrapped ETH. What the contract does at the end is, I go to all the list of possible assets, that users could ever touch. I'm gonna go in and pull like what's my balance, right? I'm gonna construct this table of like the leftover tokens because I already have carried out all the calls. And so for a swap, this will be exactly one asset, exactly the output tokens, which the user did not know how much it was exactly, right? And then the contract, the wallet contract will construct the node, right, from the anonymous address, using the type and the amount, insert the node back to the tree, right? And at that point, the user could prove that the user had the assets in the Merkle tree, right? So the wallet essentially, you can think of whatever you have, whatever smart contract operations you do. At the end, if the state is encoded in terms of ERC20 tokens or 721, 1155 tokens, that will be deposited back into your shielded pool accounts automatically by the wallet.
Got it. Thanks. That's really cool.
Well, I have one quick question. How are you doing proof of non-inclusion efficiently inside of the snark?
Yeah, so this is hard, which is the part that we actually didn't implement yet. So you'll have to prove that you have an asset that have not been spent. The part that's that had not been spent, includes basically a non-inclusion proof, right? You have to show that the notifier have not been, So I think the way to do it, like we plan to do it with a sparse Merkle tree, right? So that allows you to do non-inclusion proof. But this is bigger than the incremental Merkle tree, and maybe we can do like Merkle Patricia tree. So yet to be determined exactly how to do this. Right. It looks like they have a question.
Awesome. All right. Thank you, Wei.